Yeah, this is so cool. All right. So, yeah, what I have in front of me right here is this is called this circuit. It's so simple, the super simple circuit. It's called the Atari Punk Console. This thing was invented back in the 80s to try and teach electronics to students as a fun project to build. And, it gets its name obviously because, as you can see, the sounds that it makes are, you know, reminiscent of old school arcade game systems, right? Anyway, we're gonna do something with that. But first, there's something I've been thinking a lot about this recently. This topic, which is innovation. Yeah, what is innovation? I think in the world of software development and electronics and music even, we often find that like true innovation really is not about coming up with something from scratch, like something we've never seen before. Instead, innovation is really about combining and modifying, right? It's about creativity. It's about finding something that is already known and tried and tested and like reworking it to make something new. And what we're gonna be doing today is not gonna be groundbreaking and is not gonna be like this innovative thing. It is gonna be creative. And so what we're gonna do today is we're gonna take this circuit and we're gonna turn it into a percussive Eurorack module. We're not going to do everything in one session. Today, what we're going to do is we're going to figure out the circuit, okay, and then we'll take it from there. So, let's see. What do we need to make this sound more percussive? Well, we'll need the sound source, which we already have here. It's this circuit, and it's already on the breadboard. So we're already partway there. But then we'll also need a VCA, and we'll need an envelope generator, and that should help us. That should get us quite a bit there. I think quite far. All right. So here is the schematic for the APC. What can we do here? Well, I can tell you that one thing I can definitely do is we can use these control pins. This can take in our CV signal. Now we're gonna have to add some protection to this thing because according to the data sheet, this chip can only handle a certain voltage, and it depends on what the rail voltage is. So it has to be just a little lower than what you're supplying the chip with. Okay, so we're gonna be supplying at 12 volts. So I think a 10 volt maximum should be just fine. And this is actually beneficial for us because the Eurorack standard for CV signals is 10 volts peak to peak, which means that it could either go from -5 to +5, or it can go from 0 to 10 volts. So this whole circuit here is going to be operating with a single rail and ground. So just plus 12 volts and ground, and that's it. I'm not going to make use of the -12 volts for this particular project today. So what we'll do is we'll just do a little clamping circuit here for each one of these, and that will be the inputs for the control voltage for the frequency for each one of these astable 555 timers. If you're wondering what astable means, well, it is one of quite a few different configurations of the 555 timer. If you want to learn more, I'm going to leave some links in the comments. and you can go nuts. There is so much out there already. I don't think I need to cover this any more than it has already been covered. There's plenty of information out there for the 555 timer, the A-stable, and even the APC. But what we do need to figure out is what we're going to do with the envelope generator and the VCA for this. Okay, so I have over here 2 posts which I found for envelope generators. These are super simple, and this is actually what we're gonna do. We're gonna do something like this. Okay, let me just bring this back to this view, and here's in a simulator here a little bit about how this circuit goes. So I am right now I'm supplying a not a square but a pulse width module. Well, it's a pulse really. Well, it's not really a pulse. It is a gate. So this goes on and stays on, then goes off, but it's staying off much longer than it's staying on. Okay, so if I put the duty cycle at like 50%, then that will be pretty much a square. But I want to simulate more like a trigger, right? So this is what this looks like, right? So this right here is just for some protection. And then we're gonna get a voltage. This is gonna be coming in from some external source. We might actually maybe put a button there. I haven't quite decided yet. We'll get the circuit going, and then we'll figure out what other modifications we can make. But so the control voltage coming in just gets buffered, and then once buffered, we can manipulate it. And then once we manipulate it, we're going to buffer it again, and that's what's going to go out to the rest of our circuit. So how this thing works, right? So this is the beauty of this thing. It really just, this is the thing that's actually giving us the envelope here. And this capacitor here, right? And so what we're doing is through these 2 resistors and these 2 diodes, and notice that the diodes are in opposite directions, right? So that means that when the current is going, in this direction, it follows this path, and then it has to go through this resistor. Now, depending on where you have the wiper on that potentiometer, that's how much resistance it's going to encounter. And so that's changing that resistance will change the time that it takes to charge the capacitor, right? And once it's fully charged, then it's at its fullest amount, and then it doesn't charge anymore. Everything just goes directly into the op amp, and that's what gets sent to our circuit. Now, when we discharge, the current is going to go in this way, and it's also going to go back in this way, right? But it's going to go back in this way depending on, actually nothing's really going to, because this is like, high impedance, right? So, but it's just going to see what voltage that is at this point. And so when the current is leaving here, it's going to do it based on how much resistance it encounters. So the more resistance, the slower it'll go, right? And that's how we achieve that attack decay envelope. Okay, so now that we have this, the next piece is we need an amplifier, voltage control amplifier, right? So let's look and see here. So there are so many circuits for VCAs. Some go from very complicated, like what you see on the screen right now. Actually, this is actually simple compared to some of the other ones that I've found. This is a really good article. It has information about all sorts of different VCA circuits. I'm going to leave the link down below so you can read it at your own. But again, this is too much for us. what we do know is we want something simple, right? So well, this one says simple. What does it look like? This is another one of that OTA circuit. We could do something like this, but I want to see if there's something even simpler. So keep looking at this. This is a differential amplifier, VCA here. And this is getting a little bit closer to what we probably could use, but it still has too many parts for my liking. So let's see if we can find something even simpler. Okay, so I found this article. This is like as simple as we can get here. It just has a diode and a transistor. Now, I actually tried this out, and it was surprisingly good. It was interesting. There was only one caveat. It does distort, and it does distort quite badly and quite noticeable. And in order to get the distortion levels to a little bit more manageable, when I tested it, what I had to do was reduce the control voltage at the base for this, and the way that this is configured, and what the outcome that I got was only I was only able to get a signal up to like 1.7 volts peak to peak, which means then we would have had to take this through another stage to increase the volume of this thing, and that means getting another op amp. So we could use this, but let's see if there's anything else. Okay, so then I came across this, and this is another one of those really simple, super common things that people do. Building a VCA with a Vactrol. This is really popular because, also like this one, it could be done in a passive format. The gotcha here is that Vactrols are notoriously slow. And since we're going to be making more of a percussive thing, I wanted something with where I can at least trigger 16th notes at like a fairly fast tempo. So as this is right now in this configuration, this is probably not good enough for me. It's just going to be too sluggish of VCA. But then I encountered this, which was a little modification to this Vactrol circuit here. Just by simply adding this capacitor, we turned this into a low-pass gate. And what I discovered was this actually makes it a lot more snappy. And it makes it good enough, at least for what we're doing today. So this is what we're going to be adding to our circuit, okay? Let me talk about Vactrols real quick. Vactrols are nothing more than an LDR, that's a light-dependent resistor, and an LED. And the way this works is that as we apply current to the LED brights up, and the LDR detects this light, and it reduces its resistance, thus allowing more current through. When it's pitch black, this is like up in the mega ohms in terms of resistance. So there's nothing, almost nothing going to be going through. And so this is what we're going to be doing. I may show you guys how I make my Vactrols, although there's plenty of stuff online for this. I'll leave some links for you guys as well. So this is what we're going to be doing. So let's go back to this. So we're kind of halfway there, right? We have the APC already here. So, and with the power of editing magic. Okay, so let's see. So I've just added now the Vactrol, which has the output of output signal from the APC into the side where the LDR is. And the other side of the LDR, I've just added the capacitor that turns it into that low pass gate. The LED is on this side, and the cathode is going to ground. And on the anode side, I'm supplying current through a current limiting resistor and a 100K potentiometer. And so when I connect it to, say, I'm just going to connect it to the 5 volts, you'll see that sound will begin to hear some sound. Right, and this is because there's a very small current bleeding in, so it's actually creating enough light to let some of the sound go through. So as the LED gets louder, as it gets brighter, the sound gets louder. And this is how we're going to control our audio to make it more percussive. All right, so next I am going to add the attack release circuit to this board. Okay, so really quick recap here of what we've got going on. So we have the circuit for the APC, and and we have this little voltage divider here to give us a reference for the clamping little network here, for the CV input for each one of the oscillators of the APC. And we have the Vactrol, and then we have this attack release schematic. So I have this set up, wired up here now. Let me move the camera a little bit so that, there we go. Okay. And so the output of the APC is now going into the Vactrol, which we heard already. And this right here is TL074. Turns out I only have the 4 the quad op amps, not the 2 op amps. So maybe we can do something else with the 2. I think it might be fun to maybe have an additional envelope, maybe just release with a different output, so a different potentiometer controlling the release. And then maybe it'd be nice to have an inverted option of that, so that we can use that to send to the control voltage of this thing. So let's see what this sounds so far. So I've wired up 5 volts going into this area right here, and then it's going through a current limiting resistor down through the diode, and then it goes into the attack release network there. So let's see. So that seems like it's working. And if I change this right here, short, long, and then for the attack, But even now, we can, we can send some of these signals to the network here. So what I have right here is that little network, clamping network that I was talking about. So I'm gonna put one entry here and put the other one right there. Okay, and then I'm gonna take the same output that I'm sending to the VCA, but we'll have it control the 555 as well. Yeah, we can probably get it off of here. Okay, so what do we think is going to happen? Let's see. Now I think it might be interesting if we can invert it. So since we have those 2 extra op amps, let's do that next. Okay, so I have updated the schematic here for the attack release rather. And so this is what we're gonna do. Since we have 2 extra op amps, and I'm buffering the input signal, so it's gonna the op amp the envelope is gonna get triggered from the same gate. And since we're buffering over here, we can actually send it to this network over here, which is identical to this one, except instead of putting an attack for this one, I'm just gonna make it a release. I just don't, it's already a lot of knobs, a lot of potentiometers on this thing, and I want to keep it kind of tight. If you want to add it on yours, if you choose to do this, really easy, just do exact same thing as over here. So I'm going to get the release portion here, and then I'm going to buffer that, and that is going to be our envelope number 2. And for that 4th op amp, what we're going to do is we're going to change this slightly here, because what's happening over here, since we're only powering the op amp with plus 12 volts and ground, the inversion is going to have some kind of reference voltage. And ideally, we want to center it around 5 volts. So the easiest way to do that is to take that 500 resistor and split it into 2. Now, I actually think it might be more interesting if instead of doing this with 250K resistors and just get the 5 volts, if we just throw a 500K potentiometer here. That way, when we shift this up and down, it's gonna get some interesting things happening over here, because what it's going to do is it's going to shift the envelope either up or down, inverted. And I think that that's going to be interesting, once we send that over to the APC portion of it. So all we have to do for here is we're going to set up the op amp in an inverting configuration. And let me zoom this a little bit here. Yeah. And we don't really need to amplify it. So I figured, just some 50K resistors at the input and at the feedback should be more than enough. And, we'll throw in a resistor just because we're not going to hardwire this. This is going to be in a jack, and we may want to use it for another module. So we're going to throw some impedance of 1K in there. So really simple, right? Really simple. But this is going to give us so much more options once we get done with this. All right, so let's go put this on the board and see how it all works together. Okay, so I've gone ahead and added the last remaining pieces, as you can see. So first things first, let's go through this. So I've replaced the 500K resistor with the potentiometer. Beauty about this thing is that since the potentiometer is connected at either resistive track, either end of the resistive track, so regardless of where we turn the pot, this point right here is always going to see the same voltage. Now the wiper, that is going to be different depending on where we rotate the potentiometer, and that is going to help us with our little, with our reference voltage here for that inverting op amp configuration right here. So this right here has the output of the release. This is the second release that I've added. And then it's going to right now also to these inverting op amp. So I have one inverted going to one of the two oscillators of the APC, and the non-inverted is going to the other one. So let's see what that sounds like. Let's increase the release. Maybe let's shorten the release of just the second envelope. Right. So, there you have it. Now, of course, when we build this, we're likely not going to have things hardwire, although, I don't know, we might. Instead, what I like to do is have the outputs and inputs all be connected to jacks, so that we have more flexibility in our system of rerouting things. We could probably put a few normal ones. That's going to be the decision for the next video. And while we're speaking about the next video, so PCBWay has reached out and offered to sponsor one of the videos. So I figured for the next video, what we'll do is we're going to take this circuit we have over here, and we're going to bring it into KiCad and create some files for manufacturing. And I'll take you through that process as well. And yeah, so we'll see you next time. If you like this video, if you like this video, go ahead and hit that like button. And if you want to see more, hit the subscribe channel so you can be informed of the next video. Okay, guys, stay creative. Remember, today's topic was all around creativity, and I think we did really well. Okay, I'll see you guys in the next one. Bye.